Next, we have Yin Cui, a senior research scientist at Google. Before joining Google, he obtained his PhD in computer science from Cornell University and Cornell Tech in 2019, advised by Professor Sergey Belonji. His research interests are computer vision and machine learning, and he will be presenting a talk titled Open Vocabulary Visual Perception upon Frozen Vision and Language Models. Thank you, Yin, for agreeing to give this talk, and I'll hand it over to you now.
Thanks. So are you able to see my screen of the shared
Yes.
slides?
I
Okay,
can see
cool.
it.
Yeah. Hi, everyone. I'm Yin, and I'm a research scientist at Google. And today I'm going to talk about open vocabulary visual perception upon frozen vision and language models. So at the beginning, I would like to give a few slides about the background. So first, about vision and language models. So traditionally, in computer vision models, we do the pre-training on a fixed set of discretized labels. For example, ImageNet 1000 classes. And the downstream tasks are usually just, we use the weight initialization for this pre-training for fine-tune, and then later for fine-tuning on some downstream tasks. And we basically have no open vocabulary capabilities. But the recent trend started by OpenAI's CLIP about vision and language models basically conduct pre-training on large-scale image text pairs, for example, 400 million web text image pairs in CLIP. And in terms of the downstream transfer, due to the learned vision language alignment of the model, it can directly do zero-shot prediction on some downstream tasks. And of course, we can also do fine-tuning by using it as a weight initialization. And the figure below shows the contrastive pre-training of CLIP and how it uses a text prompt to conduct prediction on some novel classes. Okay, so I'm now going to switch gear a little bit and talk about some progress about the object detection. So in our research community, we have been spent a lot of time trying to build data set and a benchmark that to facilitate a large vocabulary detection. For example, in Pascal VOC, we had only 20 classes, but later we built Coco, which contains 80 common objects of daily life. And later, this has been significantly, the number has been significantly improved by Object 365, and also most recently LVIS dataset, which contains more than 1,000 classes basically relabeled on the same Coco images. So we see a clear trend of trying to build a larger and larger vocabulary for object detection. However, there's a big challenge, which is a long tail distribution, meaning a few dominant classes claim most of the data, while most classes have only very few examples. So based on the statistics of the LVIS dataset showing on the right, basically, we found exponentially more data might be needed for rare classes in order to have enough training examples for all the classes. So this is expensive. This is extremely expensive, especially for tasks requiring extensive annotations like detection, bounding boxes, instance masks, or segmentation and video, etc. So we are thinking, are there any alternatives to solve this issue? So we identified a direction which is also inspired by CLIP last year, by basically trying to work on the open vocabulary visual perception based on pre-trained vision and language models. So we first did an exploration on the detection via distilling CLIP's vision and text encoder. So the model is basically a masked Gaussian detector with frozen CLIP text encoder to extract class embeddings as the classifiers. And during the training, we first offline extract clips image embeddings on some cropped and resized regions from the training set. So this is very similar to what RCN did. And later, those extracted regions are used for the online training of the mask RCN. So other than the mask RCN losses, we added an additional distillation loss and train the model on the base classes. So the distillation basically tries to make sure the mask RCN region embeddings and the offline extracted image embeddings on those same cropped regions are similar. So basically, this way we can train a mask RCN that can no longer detect the fixed set of the classes, but also the novel classes described by arbitrary text. So this was presented at iClear this year, and we also have the code and demo available in GitHub, and feel free to try them out. Basically, right after this project, we also started to explore how we can do segmentation with similar techniques. So the central idea is also we try to learn some class agnostic segmentation regions from the images. So the supervision are the class agnostic segmentations showing here. So we basically remove the requirement of the classes. So you can think of this annotation is more like drawing the boundaries of the regions. And also image captions, paired image tags, basically. So I'm not going to spend too much time on this paper, but basically we train the model using the region, basically trying to align the region and the image embeddings. And the class agnostic regions are learned in a similar way as a mask former. Basically, we have some tokens as to represent the region proposals. So those region proposals have been aligned with annotations of class agnostic segmentations by some losses. Here we show on the top right figure, we show the output of such a trained model, which we named OpenSeg. So basically, you can see when we give the model different text queries, the model is able to segment the image in different ways. For example, if we have both bride, groom, and the hills and the field, we segment them out into different regions. But otherwise, if we only have like generic descriptions like couple and land, the model is able to merge those regions. And the lower right image shows how it looks like of the learned class agnostic regions. So the left one is the original image, and on the right we show some of the exemplar class agnostic regions predicted from the model. So we can see the model is able to basically discriminate between foreground and the background, and also the scuba diver and the corals. And here we can see the model is able to segment out goggles. So we have lots of those class agnostic regions, which can be used to further merge and align with descriptions provided for the model to segment. And this paper will be presented this year at CVPR in the Vision plus Language session, and we also have the code demo available. All right, so in this talk, I'm actually going to focus on how we can greatly simplify this existing promising paradigm by building the open vocabulary models upon frozen VLMs. I'm going to show two most recent work from us. along this direction. The first one is how to leverage frozen VLMs for object detection. And the paper is called F-VLM Open Vocabulary Object Detection upon Frozen Vision and Language Models. And the second one will be about how to adapt frozen VLMs to multimodal video, which will be the second part of this talk. Okay, for this work, we basically find that frozen clip encoders is actually a good localizer and a good region classifier. So we show this basically empirically by just doing some k-means clustering of the frozen clip features extracted on the image, and also the ground truth regions classified by just using the pooled features inside the ground truth box together with the pre-trained clips text encoder. So we can see here, basically by just doing the simple k-means clustering of k equals 6 on the features, we can see that the objects are described, the shapes are described quite nicely. For example, the car actually contains drastic different color parts and also the wheels, but those are all like nicely grouped together into the car object. And also here in the image below, we have different like oranges, for example, but you can see that they are not like grouped together into the same region, but has a boundary to like separate them. So we see those are like having strong potential for like doing detection and instant segmentation. And the same for the on the ground truth classification. So we see that the model are also having great accuracy by classifying ground truth regions, but this is less surprising because this is closer to the like traditional usage of zero-shot classification of the pre-trained clip. And by our method, we can greatly enhance the model's prediction by adding the instant segmentation masks and also the much more richer predictions than the ground truth annotations in LVIS dataset. Okay, so basically inspired by those observations, we developed F-VLM. So shown here. So basically during training, I will not go into the details of all the boxes, but the main idea is that during training, we just only train a lightweight detector with last classification layer replaced by the base category text embeddings from the clip's text encoder. So the detector head actually contains the RPN, FPN, and the mask RCN heads. So basically everything that is not included in the original image encoder. So those are the trainable. And the pre-trained backbone is frozen. So this is just regular training as the detector, same as the mask RCN model on base classes. And during inference, we actually leverage those region proposals output from the mask RCN model, and then use the predicted region to crop the feature map and pull a feature in this region. So this is very similar to ROI align. And then after that, we add a VLM pooling layer, which is a simple cross attention layer used in Clip's backbone. And those detection scores are directly output from the detection head. So we basically use a geometric mean to average those detection scores and the VLM scores. So why we use VLM score is basically we found sometimes the VLM score works better usually for the classification, but the detection score directly output from the mask RCN usually works better on scoring how good the region is in terms of the localization. And we found the geometric mean of them actually gives a good results for the open vocabulary detection. So here, since we can use arbitrary inputs to the text encoder, we can use any novel categories that are not appeared during the training to detect novel categories. Okay, so we conducted extensive experiments on the LVIS open vocabulary benchmark by using the base classes as the combination of frequent and common classes in LVIS, and there are 866 of them, and they have at least 10 training images per class, up to about 2,000 images per class. So this is a very imbalanced training set, but we didn't do any thing to like address this imbalance issue. And for the novel classes, we basically use the rest 337 rare classes, and each of them has less than 10 images per class. So the result is that we can achieve state-of-the-art on this benchmark by training on the base and the eval on the novel classes. But at the same time, we don't need any distillation, and we also don't need to train the backbone. So this greatly simplifies the system and reduces the training cost. So next, we conduct cross-dataset transfer by using the LVIS base model to directly evaluate on COCO object 365 and Eagle 40. So for Eagle 40, we don't have any numeric metrics, and here we just include the examples as a visualization. But in summary, we are also able to successfully transfer to COCO and object 365 dataset and outperforming previous method or comparable with them when using a similar backbone. And finally, I want to mention about the training efficiency of our model. So when compared with our previous work, VIOD, we can see that our model can achieve about 14 times or more than 200 times less training cost. So this is measured by TPU v3 per core hour. So basically, the best VIOD model requires 8,000 core hours. But here, for example, our lightweight model, which actually obtains similar performance, only requires 35 TPU core hour. So this shows a great potential for our model to be incorporated with like a larger or gigantic VLMs than CLIP for both fine-tuning for the detection or just co-training by basically using detection as part of the giant model. Okay, so a second part is about how to use the frozen VLMs and adapt it to multimodal video. So the paper is, so our method is called MOV, Multimodal Open Vocabulary Video Classification via pre-trained vision and language models. So here we first conduct some initial experiments and found that frozen VLM is also a very good video classifier. So the benchmark we use is Kinetics 400 video action classification. And here, similarly, we use the frozen clip text encoder to extract class embeddings and treat them as classifiers. Basically, we just fix the last layer of the linear classifier. And we also use frozen clips vision encoder to extract frame level features. We basically treat the video frames as images. And under the similar evaluation setting with previous method by using, similar number of views and sampled frames, we show that, for example, if we just directly use the pre-trained clip VIT-B16 and just use an average pooling of all the frame features and the 80 ImageNet prompt template. So this is basically the way that clip conduct ImageNet zero shot, but we just add an average pooling of all the features on the kinetics evaluation set and see how is the performance. So basically the performance is about 55. And we think this is great actually, because this kinetics dataset is a very challenging dataset, and there should be some domain gap between the training and between clips training data and this video dataset. But here, secondly, we also use 28 video prompts, which were used by Clip for classifying video actions. And here we found the performance can be boosted by about 4.4, which is a huge boost considering the fact that we only changes the prompt used for this model. So this means that the prompt is also very important for this video task. And in the third row, we instead of direct zero-shot evaluation, we use the linear probing. Basically, after the average pooling, we train the linear classifier. Not the linear classifier, because the linear classifier is actually the fixed class embedding. So we basically insert a linear layer after the average pooled feature and before the fixed linear classifier, and train the model. So only one linear layer is trainable. And here we see a huge boost of 15.2 accuracy on kinetics. So this is actually very surprising, and this shows that a simple adaptation on the model, even a linear layer domain adaptation of the model, is able to greatly boost the performance of Clip's feature. And finally, we go one step further. Instead of using average pooling, we add a transformer head, trainable transformer head on top of the frame features, and after that we have the average pooling and the same prompt and the linear training. And we are able to further boost the performance by 2.7. And we believe this boost comes from the fact that we do the transformer modeling of the temporal aggregation, because there might be some cross-frame motions or some informations that need to be captured by the model instead of simple average pooling. And this result is quite strong because if we compare with some video specific model on this kinetic dataset, for example, slow fast is a very strong model based on ConvNet, and also Timesformer and the Vivid. Those are all based on the VITB, basically the same backbone as ours, but they did some specialized modification for the video data, and all of the models conducted end-to-end training with the ImageNet pre-training. And we can see that actually the result doesn't show a huge improvement compared with our simple baseline with just linear layer training. So that's why we believe, okay, so frozen Clip is a very good video classifier, so we should build something upon it. So yeah, like I mentioned in the previous slides, we use a frozen Clip for video to basically simplify the pipeline and reduce the training cost to make the model lightweight. Since here we only have the transformer layer, so one transformer block and one linear layer trainable. But for the audio and the motion, so certainly we cannot use frozen Clip vision encoder because the data is quite different from Clip's training set. But we know that audio and motion naturally coexist with video, so it should be complementary to the RGB pixel information. So here we use, instead of the frozen backbone, we use a pre-trained Clip with fine-tuning for audio and motion. So specifically, yeah, and we didn't modify actually the Clip's vision encoder. So we just use the same vision encoder. So specifically for audio spectrogram, we duplicate the one channel spectrogram into a 3-channel image. So that we can directly use pre-trained vision encoder. And in terms of the positional encoding, we just bilinearly interpolate it to make sure the model is able to fit. And for the optical flow.
Sorry to
Yeah.
interrupt. I just want to let you know that you have about 4 minutes left.
Okay, yeah. And in terms of the optical flow, so the flow is a 2-channel XY motion image, and we zero pad the 3-channel and make it a 3-channel image. So first we found that fine-tuning VLMs for multimodal open vocabulary video on kinetics and VGG sound datasets, basically train on base and eval on base and the novel classes, have some interesting observations shown on the figure below. So in summary, all modalities are able to improve on base classes, but with base class training, flow and audio can generalize to novel classes during the training of the model, but video cannot. For example, for video, when we have improved the base, we have decreased the novel. But for the flow and the audio, the base and the novel performance are always increasing. So this is an interesting observation. So we based on this observation to build the model. So basically, during the training, we have the video and the flow or audio. So video has a frozen encoder and the flow has fine-tuned encoder. But here we design an asymmetrical cross-attention fusion to fuse the multimodal information. So for video, we want to leverage its strong feature directly from the backbone. But for the other modality, we want to leverage its trained feature after the fusion because it does show better generalization on novel classes. So here you can see the cross attention is asymmetric. And by doing this, we are able to build a model that can use a flow and audio to improve the video classification on both base classes and the novel classes. So here we show the results on kinetics, which contains video, flow, and text, and the VGG sound, which are video, audio, and the text. So our method outperforms both the strong multimodal training VET, a frozen clip, and also recent clip adaptation methods like co-op and the clip adapter on both base and the novel classes. And here we also show the scalability of our model by using stronger VIT-L14 backbone. And basically we can see that clips improvements on the larger backbone can translate well on the novel classes of our model. So these are some analysis of what are the classes that improve most and least by introducing additional modality. For example, on kinetics, when we introduce flow modality, actions like yawning, throwing softball, long jump got improved the most. But for example, like looking at a mirror and the geocaching are decreasing because I think the motion informations are less clear or confusing in those classes. On VGG sound, so we can see nose blowing, lines rolling, belly laughing, those like very classes contain very signature sound. So it got improved a lot. But for example, like wind noise, cat hissing, sloshing water, those noisy like sound classes are got like a little bit decrease. Okay. So finally, we show the cross-dataset transfer on UCF and HMDB by using the flow and the video pre-trained on kinetic-based classes. So I would not talk too much about the details, but in summary, our method achieves state-of-the-art result, outperforming both traditional zero-shot method and the most recent clip-based adaptation method by very large margins. And here are the two figures from the paper-based code. So we are able to improve the previous LVIS on UCF by 15 point accuracy, and on HMDB more than 20 improvement.
Yin, sorry to interrupt. Oh, okay, last slide.
Yeah,
I'll let
yeah,
you finish.
yeah.
Sorry.
Yeah, last slide. Yeah. So basically, in conclusion, we show that utilizing pre-trained VLMs has become a promising paradigm for open vocabulary visual perception. And actually, it's possible to greatly simplify the paradigm by directly building upon frozen VLMs with minimal modification, showing these two works. And also, other than being performant models, we have additional advantages like reducing the training computation and memory, and also the potential for scaling to larger foundation models and co-training with foundation models. And yeah, I will finally like to thank all the co-authors. Thank you.
So thank you so much, Yin, for this great talk. We're slightly running over time, but I'll quickly ask you one question before we move on to the next talk.
Sure.
In the F-VLM model diagram, I noticed that like a lot of the the multimodal fusion happens like very late in the model, right? It's basically just the classification layer that you're replacing with the text embeddings. And so like the actual interaction between image and text, as I understand it, is like basically in the end of the model. Do you think it would benefit from like having fusion deeper in the model, or do you think it would like influence the RPN too much such that the generalization would be hard from base to novel classes?
Yeah, I think that's a great idea, but I believe it might be hard because based on my experiences, there's a difficult balance between base and the novel class performance. So yeah, in many times, if we train too much or adapt too much to the base classes, we lose the generalization ability from the clip model on novel classes. Similar phenomenon in the video I shown in the second part. So I think co-training with such model like clip can probably like solve this issue.
Got it. Okay. Thanks for answering my question. And thanks for the great talk again.